let us continue our discussion on the operational amplifier in this workshop. We will talk about the different operational amplifier parameters which help to design the circuit using our op amps. One of the important parameter is the input offset voltage, and the other one is the input offset current. So we can say that input offset voltage and input offset current are due to the variations in the electrical characteristics of the two transistors that are used in the differential amplifier circuit. Ideally, the input offset voltage and the input offset current should be zero, but there will be some variation. If you see here, there is a current flowing IB minus into the inverting terminal and IB plus flowing into the non-inverting terminal. Both of them should be ideally very less, and they should be equal, but due to the characteristics of the die, the transistors and the other circuitry around, there will be some offset current that is observed. So this offset current mainly affects the output voltage. The offset voltage and the offset current affects the output voltage, and hence we see that there is an offset on the output voltage as well. The output offset voltage basically gets amplified because of this gain. So to calculate the output offset voltage, basically it is the sum of the offset voltage produced due to the input offset voltage and the offset voltage that is produced due to the input offset current. So that is the total offset voltage that is observed at the output. Now, as we said here, there is a bias current that is flowing into the inverting terminal and non-inverting terminal. So if you see the data sheet of the operational amplifier, the bias current is given by the parameter that is mentioned in the data sheet is the input bias current, and it is not the individual bias currents into the inverting and non-inverting terminal. You have a parameter called input bias current. So this input bias current parameter is nothing but the average of the currents flowing into the bias currents flowing into the inverting and non-inverting terminal. That means the bias current is given by IB plus IB minus by 2. So if you want to individually calculate the offset currents from those, you need to use this formula. So these are some of the parameters. If you take an ideal operational amplifier, all these would be zero. But in practical, there will be some millivolt in some operational amplifiers, microvolt in some operational amplifiers. The offset current would be in nanoamps. So these affect the usage of operational amplifiers in the real-time circuits. Now, some op amps will have like a very low offset voltage and current, while some op amps have high offset voltage and high offset current. So depending on your application, depending on the accuracy that you need over the output, we select our operational amplifier. Then one more parameter of the operational amplifier is the gain bandwidth product. Basically, we have seen that the model of an operational amplifier can be represented this way, where V1 and V2 are the inputs. VID is the difference between V1 and V2. So this VID is multiplied by gain and is given as the output voltage. So the output voltage is defined as A into VID. So A is called the gain here. So the operational amplifiers, if you take, have very high gain and high bandwidth. So this gain can be classified in two types. One is called the open loop voltage gain, and the gain we are talking here is basically the voltage gain. So it is open loop voltage gain and the closed loop voltage gain. So open loop voltage gain is very high because there is no feedback, and whatever is mentioned in the data sheet is the open loop voltage gain, and it is the maximum voltage gain that can be achieved by an op amp. Whereas closed loop voltage gain is nothing but there will be the gain that can be achieved by an op amp which has a feedback. So the feedback helps us to stabilize the operational amplifier and have a limited gain such that the operational amplifier doesn't go out of hand. So that means it doesn't go into an unstable condition. So we will talk about what is gain bandwidth product in the next slide. So here we have had a glimpse of open loop voltage gain and closed loop voltage gain. Now, this closed loop voltage gain, before going to the gain bandwidth product definition, we said in the previous video that the closed loop voltage gain is high, and then we add a resistor such that in the feedback, that means from output to the input, we add a resistor which is called the feedback resistor, such that we have a stable condition, a limited gain, and then one of the advantages of having these feedback resistors is that it varies the input impedance. It increases actually, and then the output impedance will be reduced. So what is the advantage of this is we know that ideal operational amplifier has a infinite input impedance and zero output impedance. So the better the input impedance and lower the output impedance, better the operational amplifier performance. We know that because when you have a high input impedance, there will be very less load on the source you are connecting. Whereas if you have a very low output impedance, the operational amplifier can provide better output to the load. So considering this scenario, the feedback condition of these operational amplifiers, whether it be increase in input impedance or reduction in the output impedance, which is achieved by feedback resistor, is very good. So if you see in general, that is why the operational amplifier, if you are using, will have a feedback which operates the feedback in a which operates the op amp in a stable condition. And one of the major advantage is that the frequency response of the operational amplifier is also better when you have a feedback resistor. Coming to the gain bandwidth, so basically what happens is you can provide as much frequency to the op amp as possible. Now what happens is as the frequency increases, the gain of the op amp reduces. So that is what you observe here. This is the frequency and this is the gain here. So the open loop voltage gain of a op amp reduces with frequency. The reduction, as you see here, is 20 dB per decade. So for every decade change of frequency, you have a 20 dB voltage down. That's what the slope meant here. Now the gain bandwidth product is nothing but the product of the open loop voltage gain and the frequency and the frequency is nothing but at which the gain has fallen 3 dB down from the maximum open loop voltage gain. So if you see here, example 110 is the maximum voltage open loop voltage gain here. So a 3 dB drop from here is achieved at f3 dB, which is in between 10 Hz to 100 Hz. So the gain bandwidth product is given by the value f3 dB into g3 dB. So that is what a gain bandwidth product so represents. So in data sheets you see this and this is what you use for your design. And then there is one more parameter that is also represented in the data sheets, which is called the unity gain bandwidth. The unity gain bandwidth product is nothing but the frequency, the product of the frequency at which the gain falls to unity, that means single. So when the gain is unity, still you can use an op amp, right? Because instead of amplifier, you use it as a voltage follower, but still op amp functionality can be used. So that means you can see here the range from 1 to whatever in between 1M and 10M. This is called the bandwidth of the operational amplifier. Whereas the gain bandwidth product, as we mentioned, is nothing but the product of voltage gain, open loop voltage gain into frequency at which the gain has fallen 3 dB from the maximum open loop voltage gain. So this is very important parameter while you determine the maximum frequency at which you can operate the op amp, considering a gain, a stable gain from it. And then there is one more parameter called slew rate. Slew rate defines the rate at which the output operational amplifier can change. Example, if you see here, we have given an input of a square wave to this op amp, and you can see the output changes slowly considering the slope delta V by delta T. So ideally, when you give an input like this, the output also should be a square wave, but it slowly changes, rises and slowly falls. So there is some slope associated with a sudden step change here. So this sudden step change cannot be achieved at the output directly. There is a gradual variation that is seen at the output rather than sudden step change. So this variation, the maximum rate at which the amplifier output can change, is called the slew rate of the operational amplifier. Slew rate is defined by volts per microseconds. So what it means is that so if you see here, till this moment, example, if you take this case, till this moment the input cannot change. It should still be at a high level and little more than that, so that you can read the value. So that means the input signal cannot go down below this value, which means the frequency of the input is determined by the slew rate. So the input variation of the op amp is restricted by the slew rate, and it is one of the important parameter which we need to look into the data sheet of the operational amplifier. And continuing our discussion, there is one more point which we need to remember in op amps. Let us take a scenario where we did not give any feedback to the operational amplifier. We just provided some voltage to the inverting terminal and we just provided some voltage to the non-inverting terminal. In this case, as the feedback is not provided, this simply acts as a comparator. So we will see the comparator in the next videos. For now, remember that the guys who are experienced can easily understand what is comparator here, but the guys who are novice and just trying to understand, remember that it acts as a comparator, and we'll discuss about comparator in the next video. So as it acts as a comparator, what happens is the output goes to a maximum level, which is VCC, or it goes to a zero level. So there will be variation from 0 to VCC based on the inputs provided on the inverting and non-inverting terminals. So if the non-inverting terminal has a voltage higher than the non-inverting terminal, there will be a high voltage. When the non-inverting terminal has a high voltage than non-inverting terminal, there will be a low voltage. So that's how this comparator works. In next videos, we'll see the comparator functionality. See, these are the different parameters which are used in op amp, and which are all the parameters which will be listed in the data sheet, and how they can how we can use understand these parameters and use in our circuit designs. Please comment if you have any questions or if you have any concerns on this video. Thanks for watching. Thank you.